Hello and welcome. Today we will be talking about Minimax. Minimax is a basic decision-making algorithm for determining a move for an artificial intelligence in an adversarial game. Before we dive into the actual algorithm, it's important to develop a basic understanding of how the underlying theory comes into play. First, what is an adversarial game? An adversarial game is effectively what you see in a large majority of your classic two-player board games, such as chess, Othello, backgammon, checkers, etc. In a classic adversarial game, there are two players who are opposing each other. Each player's goal is to win the game while simultaneously denying a win to their opponent. In Minimax, there are two opposing players in the decision-making tree. The tree containing the current game state and all of the future game states. These opposing players are the minimizer and the maximizer. The goal of the minimizer is to reach an end state with a minimum value for its given heuristic, while the maximizer desires an end state with the maximum heuristic value. For our example, we'll be using a very simple adversarial game, tic-tac-toe. Interestingly enough, even though we consider tic-tac-toe to be a relatively simple game, there are many different ways for the game to end. So let's just draw a tic-tac-toe board. So we can draw a number for every single position on the board. So if we were to fill up the board place by place without stopping for a win state, we can see that there's 3 to the 9 possible board configurations. And that's because we have X, O, or empty for each of the 9 spaces on the board. So all in all, that's nearly 20,000 configurations, even for what many of us would consider to be an extremely simple game. So for our game, we'll start from a game that's already in progress to reduce the number of states, because I don't want to draw out 20,000 circles for a tree. Before we start building the tree, though, it's important to understand that Minimax makes several assumptions about the game. The first and probably most important assumption is that each player plays the game optimally. At this point in my video, I have switched from doing the board drawings and the vocals separately and just doing it all in one. So sorry about that. Okay, so what that means is that each player would always choose the very best move in order to get to the very best end state for that player. So this means that each player knows what the other player will do, since both players in the game play optimally. Interestingly, this means that if both players are playing optimally and each perform Minimax all the way to the end of the game before the first move, the game is already over before a single piece is laid and the winner is already decided. So I like to think of like two androids sitting at a chessboard and looking at the board, and then one looks up and says checkmate in 47 moves, and the other says good match, want to play again. And this is kind of effectively what the case of two optimal players playing against each other means. So androids aside, the first step of performing Minimax is to develop our heuristic. For this example, we'll create a simple heuristic. What we'll say is that, oh dang it, I did it again. O wins. We'll give that a value of -1. X wins. We'll give it a value of 1, and we'll say a tie is 0. O, in this case, will be our minimizer. because it wants the end state of a value of -1, which is the minimum possible end state, right? And x will be our maximizer. All right. And we're choosing a tie to have a value of 0 because if given a choice, the minimizer will choose a tie over x winning, and the maximizer will choose a tie over O winning because it's right in the middle of the two. For our example, we're going to create a little board where each player has already moved twice. Thrice. Each player has already moved 3 times. And it's now X's turn again. So that's because X always goes first in tic-tac-toe. And so we need to make a tree of all the possible game states down from this point. So we're just going to draw that in real fast. All right, so the root of the tree is the current state of the game. And since there are 3 open spaces X can move, we're going to have 3 branches coming off from the root. And I have done that again. I am doing that every single take, I swear. All right, so we have 3 branches coming off, and we're going to make our little boards like so. All right, and we're going to fill them in. I guess I could have copy pasted this. It probably would have been faster, but just going to go with it. Okay. All right. And then, you know what? I'm just gonna copy paste. Grab them like that. Copy. Okay. And then, so we've got the 3 branches from the root, and then each of these nodes has 2 places O can move, followed by 1 more for X. So I'm just going to paste a bunch of these. Pause real quick. All right, so I've gone back. I fixed the tree. Everything should be good. I've rotated it. Perspective's a little bit weird going from it being on the side, but since it's, you know, all squares anyways, no big deal, right? So I've also drawn out this little guy over here, which is, we are going to use this for the minimizer, maximizer values. So we can actually like take a look at the tree. All right, oops, scrolled it down. Let's go back up. All right, so first thing we're going to do is we're going to label these turns. So the maximizer's at that layer, minimizer at that layer, maximizer again at that layer. All right. And we go down to the bottom of the tree, grade all of them based off of our heuristic, and then go back up. But there's some things that clearly just shouldn't be in the tree at all. So a good example would be right here. We've got 3 X's across. So naturally the game would end at that point. So we're just going to say that we made our heuristic smart enough that it'll stop the game as soon as there's a win. Okay, so there's a win there, right? And this one doesn't have any wins. There's a win there. Okay. There's a win there. Win there. Win there. And win there. Okay. So there's no ties, which is interesting. That was not an intentional design choice. Oh, there's also a win there. So let's go back up. Oh, there's where the win actually occurs. So all of this can be removed. And okay, cool. Yeah, so that wasn't an intentional design choice. But here we go. We're going to erase some of the extraneous branches out of here, which is, in this case, everything. Let's make that bigger. That's like a raindrop in the ocean right there. Okay. Okay. So now we've got our tree as it will actually functionally progress in the game, because let's hope that our heuristic is smart enough to actually end the game when we hit a win state or when we fully populate the board. All right, so let's go to all of our leaves and check them. So first one is this one right here. So that is an O win. So that's going to get a value of -1. Okay. And then this one is an X win. So that gets a value of 1. X win, X win. Everything else is an X win at the leaves. So they're all 1s. All right. So we're going to bubble these back up. So there's no choices here. So this is going to be a 1. That's going to be a 1. That's also going to be a 1. All right. So right here, it's Min's turn, right? So Min's choice is going to be the one to bubble up here. Min gets to choose between a -1 and a 1. Obviously, Min, looking for the minimum, is going to choose the -1. All right. This one, you're choosing between a 1 and a 1, so it's going to be a 1. Min doesn't have any choice. And then this one, there's no choice. And then the maximizer, at this level, chooses between the 3 children. We have -1, 1, and 1, so it's going to choose 1. Now, how this actually progresses is going to be, based off of the actual algorithm itself and how you decide to actually do it, but we're just going to assume that it's going to kind of do depth first, and it's just going to go with the first win that it encountered, which is this one. So what this is saying is that X, if it moves here, so it populates an X in this location, it knows that it will win. In fact, it will win no matter what. Because no matter where the O is placed in the following move, so there's 2 spaces left here and here, O can be placed there or O can be placed there. It doesn't matter because X will win by either completing a line there or completing a line there.